Right now, 250 feet beneath the English Channel, engineers are building something that makes the Channel Tunnel look like a subway, 4 kilometers underwater, deeper than Mount Fuji is tall, where water pressure would crush a human in milliseconds. Yet engineers work here daily, reshaping the ocean floor. These aren't just construction projects, they're humanity's boldest declarations against the ocean's absolute authority. Every tunnel segment lowered into crushing depths represents thousands of calculations, backup systems, and the kind of engineering audacity that turns science fiction into commuter routes. We're literally punching holes through the planet's most hostile environment and making it safe enough for your morning drive to work. But one underwater project went so wrong, it's still classified 20 years later. Today, we're counting down humanity's most insane underwater achievements. Projects that make the impossible look routine, where engineers didn't just solve problems, they rewrote the rules of what's humanly possible, from tunnels that connect continents to construction sites deeper than the Titanic's grave. These are the 10 most psychologically demanding underwater projects ever attempted. Picture this, you're driving across a bridge when suddenly the road dives underwater and becomes a tunnel. The Øresund connection between Denmark and Sweden starts as a bridge but transforms into a tunnel to allow ships to pass overhead. Engineers faced an impossible choice: go over the shipping lanes and block massive cargo vessels, or go under and risk a catastrophic flood. Their brilliant solution defied conventional engineering wisdom. They did both. The bridge literally sinks into the ocean, becoming a tunnel through an artificial island called Fehmarnbelt. Workers had to create a seamless transition point where cars traveling 80 miles per hour suddenly find themselves in an underwater tube. The artificial island was built using 7 million tons of material dredged from the sea floor, and construction crews worked in rotating 8-hour shifts because of the psychological stress of constantly switching between above water and underwater work environments. This hybrid approach would set the stage for even more ambitious projects, but nothing could prepare engineers for what came next: a tunnel that would require them to work under pressure that could liquefy human bones. This isn't just a bridge, it's a 34-mile sea crossing that includes the world's longest underwater tunnel section built in open waters. Imagine the pressure. You're 157 feet underwater, where the weight above you equals 10 elephants, standing on every square inch of your body. The impossible challenge was building a tunnel through a shipping channel so busy that stopping maritime traffic wasn't an option. Plus, the tunnel had to withstand typhoons with winds over 200 miles per hour. Engineers created their miracle using 33 massive tunnel elements, each weighing 80,000 tons, heavier than the Eiffel Tower. Each section was built on land, floated out to sea, then precisely lowered into a pre-dredged trench with millimeter accuracy. Workers wore emergency escape suits that could keep them alive for 45 minutes if the tunnel flooded, while emergency rescue chambers were positioned every 500 meters, equipped with independent air supplies and communication systems. The tunnel elements were so massive that special ships had to be built just to transport them, and construction crews worked in 6-hour shifts due to pressure limits and psychological stress. Yet even this engineering marvel pales compared to what Japanese engineers attempted next, a project that would take them to depths where the ocean itself becomes an enemy. Nearly 800 feet underwater, this is deeper than the Titanic wreck. Workers here experienced pressure equivalent to 34 atmospheres. Imagine being crushed by the weight of a small building pressing down on every inch of your body. The impossible challenge was connecting Japan's main island to Hokkaido through the Tsugaru Strait, one of the world's most geologically active underwater zones, requiring an earthquake-proof tunnel built through active fault lines. Engineers solved this by creating an underground city 450 feet down with machine shops, medical facilities, and rest areas. They used specialized concrete that could flex during earthquakes and developed new steel alloys that wouldn't crack under extreme pressure changes. The construction methodology involved first boring pilot tunnels to test geological conditions, then excavating main tunnels using the NATM, New Austrian Tunneling Method, installing waterproof concrete lining in sections, and finally building rail systems with flexible joints for earthquake resistance. During construction, workers encountered underground hot springs, with temperatures reaching 105 degrees Fahrenheit, and the tunnel now has its own weather system. Engineers had to install climate control to prevent fog formation that could blind train operators. While Japan was conquering geological nightmares, European engineers were about to attempt something that would redefine the very concept of underwater construction. This was humanity's first serious attempt to punch a hole through the ocean floor between two countries. Engineers worked 250 feet underwater, where pressure reaches 108.2 psi, enough to turn air into liquid if containment failed. The challenge seemed impossible. Tunnel through 31 miles of chalky seabed, while keeping millions of gallons of seawater from flooding the construction site. The solution required revolutionary tunnel boring machines weighing 15,000 tons each, cutting through rock while simultaneously installing concrete rings to prevent collapse. Workers faced claustrophobic conditions in tubes barely wide enough for equipment, with emergency escape routes every 1,200 feet leading to service tunnels. The psychological impact was severe. Imagine being trapped 300 feet underwater in a concrete tube, yet this tunnel now moves 50,000 passengers daily through the ocean floor. Construction crews developed specialized decompression chambers and worked maximum 4-hour shifts due to pressure-related health risks. But as impressive as the Channel Tunnel seemed, engineers in Turkey were about to attempt something that would dwarf even this achievement in both depth and ambition. The Marmaray project achieved what seemed impossible, connecting Europe and Asia underwater through the Bosphorus Strait. At 197 feet below the surface, workers faced not only crushing pressure, but also the psychological challenge of literally connecting two continents beneath one of the world's busiest waterways. The engineering challenge was staggering, tunneling through soft marine clay that could liquefy at any moment while avoiding damage to 8,000-year-old archaeological sites discovered during excavation. Engineers used ground freezing technology, pumping liquid nitrogen through pipes to turn the clay into solid ice, creating temporary walls strong enough to work behind. The tunnel segments were built using ultra-high-strength concrete, reinforced with specially designed steel mesh that could withstand both water pressure and seismic activity. Emergency evacuation procedures included pressurized escape pods that could transport workers to the surface in under 3 minutes, and construction sites featured decompression chambers capable of treating up to 20 workers simultaneously. The project required workers to adapt to a unique psychological challenge, knowing that a mistake could flood not just a tunnel, but potentially damage the connection between two continents. As remarkable as connecting continent sounds, Japanese engineers were simultaneously working on a project that would test the absolute limits of underwater construction psychology. Japan's underwater highway through Tokyo Bay represents perhaps the most psychologically demanding construction environment ever created, building a tunnel for cars through an active earthquake zone beneath one of the world's most crowded waterways. At 98 feet underwater, workers faced constant pressure of 42.4 psi, while knowing that any seismic activity could trap them beneath millions of tons of water and concrete. The engineering solution required revolutionary, flexible tunnel segments that could move independently during earthquakes without breaking the waterproof seal. Each tunnel section was built using a steel concrete composite that could bend up to 6 inches without cracking, while computer-controlled pumping systems could remove 50,000 gallons of water per minute if flooding occurred. Workers underwent specialized psychological training to handle the constant stress of potential earthquakes, and construction protocols included real-time seismic monitoring with automatic evacuation procedures. The most mind-bending aspect was the construction of Umihotaru, an artificial island in the middle of Tokyo Bay, serving as both a rest area and emergency staging ground. Workers had to overcome the psychological challenge of building an island from nothing, then tunneling beneath it into increasingly dangerous depths. While Japan was mastering earthquake-resistant underwater construction, Norwegian engineers were about to push depth limits to their absolute breaking point. Welcome to the deepest underwater road tunnel on Earth, where Norwegian engineers descended 1,296 feet below the surface, deeper than the Empire State Building is tall. At this depth, pressure reaches 561.5 psi, equivalent to having 56 elephants standing on every square inch of your body. The psychological impact on workers was so severe that construction protocols required mandatory psychological evaluations every 30 days and limited underground shifts to just 4 hours. The engineering challenge was unprecedented, creating a tunnel through granite so hard it dulled diamond-tipped drilling equipment within hours, while managing water inflow that could fill an Olympic swimming pool in minutes. Engineers solved this using controlled blasting techniques that created precisely shaped caverns, followed by immediate installation of steel fiber reinforced concrete capable of withstanding pressure that would crush submarines. The ventilation system had to be completely reimagined. Conventional systems couldn't handle the pressure differential, so engineers designed a network of pressurized chambers that gradually adjusted air pressure as vehicles descended and ascended. Emergency protocols included pressurized rescue pods and a revolutionary safety system where the tunnel could be sealed in 60-second segments if flooding occurred. Norwegian depth records were impressive, but they pale compared to what engineers accomplished next beneath the Bosphorus Strait. The Eurasia Tunnel burrows 347 feet beneath the Bosphorus Strait, making it one of the deepest underwater automotive tunnels ever built. Workers faced pressure of 150.3 psi while tunneling through soil so unstable it required freezing the entire construction zone with liquid nitrogen to prevent collapse. The psychological challenge was immense. Imagine working in temperatures of -40 degrees Fahrenheit while knowing that 347 feet of water pressed down above you in ground so soft it could turn to quicksand at any moment. Engineers developed a revolutionary twin-tube design where each tunnel could serve as an escape route for the other, connected every 164 feet by cross passages equipped with blast-proof doors. The construction methodology involved creating an underground refrigeration plant that kept 50,000 cubic meters of soil frozen solid during excavation. Workers wore specialized thermal suits while operating in the frozen construction zone, and emergency procedures included heated rescue chambers and thermal rehabilitation facilities. The tunnel's ventilation system processes 2.5 million cubic feet of air per hour, creating artificial atmospheric pressure to counteract the crushing force of water above. As engineers mastered extreme depth and freezing techniques, they began to envision projects that would stretch the very definition of possible. The Fehmarnbelt tunnel between Denmark and Germany represents the longest underwater rail and road tunnel in the world, stretching 11 miles beneath the Baltic Sea. At 131 feet underwater, with pressure reaching 56.7 psi, this project pushed psychological endurance to breaking points as workers spent months in an underwater construction environment. The impossible challenge was creating a tunnel longer than Manhattan through seabed, containing unexploded World War II mines and shifting sand dunes. Engineers solved this using 89 massive tunnel elements, each 700 feet long and weighing 73,000 tons, built in a purpose-constructed factory, then transported by specialized vessels. The construction process involved dredging a 65-foot deep trench in the sea floor, lowering each element with precision hydraulic systems, then backfilling with millions of tons of sand and rock. Workers faced unique psychological challenges, including claustrophobia from working inside tunnel elements during transport, pressure adaptation stress, and the constant awareness that they were building beneath active shipping lanes. Emergency protocols included submarine rescue vessels and pressurized evacuation chambers capable of bringing workers to the surface in under 10 minutes. While the Fehmarnbelt pushed length boundaries, engineers were simultaneously developing concepts that would make even these achievements look modest. This is the engineering project that exists at the very edge of human possibility, a 4,000-mile underwater tunnel connecting New York to London. At its deepest point, 4,920 feet below the ocean surface, pressure would reach 2,132 psi, enough to compress steel into diamond. The psychological impact on workers would be so extreme that entire new fields of underwater psychology would need to be developed. Current concepts involve vacuum tube technology, where passenger pods would travel at 5,000 miles per hour through airless tunnels, reaching London from New York in just 54 minutes. The engineering challenges are mind-bending. Tunnel segments would need to be built from materials that don't yet exist, capable of withstanding pressure that would instantly crush current submarines. Construction would require underwater factories stationed along the route, autonomous robotic systems capable of working at crushing depths, and revolutionary life support systems for human oversight crews. Emergency protocols would involve submarine cities positioned every 200 miles along the route, each equipped with pressurized living quarters and medical facilities capable of treating decompression sickness from depths never before survived by humans. The construction methodology would involve building tunnel segments in space-like conditions, using materials stronger than any currently known alloy, with backup systems for backup systems, because failure at these depths means instant death for everyone involved. The transatlantic tunnel represents the ultimate test of human engineering ambition, a project so psychologically demanding that it pushes beyond current human endurance into the realm of what we might achieve if we're willing to evolve our very understanding of what's possible. Every underwater tunnel we've built so far has been practice for this ultimate challenge, where engineers don't just battle pressure and depth, but the fundamental limits of human psychology itself. From the Øresund's hybrid innovation to Japan's earthquake-resistant marvels, each project has taught us that the ocean's greatest challenge isn't technical. It's convincing human minds that the impossible is simply another engineering problem waiting to be solved. When you drive through any underwater tunnel today, remember that you're experiencing the direct result of engineers who looked at crushing depths, deadly pressure, and seemingly impossible challenges, then said, "Let's build something here anyway." These titans beneath the waves prove that human ingenuity doesn't just conquer impossible depths, it transforms them into the infrastructure of our connected world. The psychological impact isn't just on the workers who build these marvels, it's on all of us who realize that if humans can reshape the ocean floor, perhaps there truly are no limits to what we can achieve.